Okay, this was one of our really fun problems, I think. This was the idea of a siphon. And how a siphon works is that, let's say you have two containers like this. And let's say you have water in one of them and no water in another one. If you take a tube and you fill the tube with water. So we're going to fill the tube with water here. So this whole thing here is water, and this whole thing here is water. So we can now apply hydrostatic equilibrium to this problem. We notice that the pressure at this point is 1 atmosphere. It sort of has to be because that's the air. So we talked about the fact that if you tried to do this in different conditions, this would be a very different kind of problem. And we also know that the pressure at the bottom is greater than 1 atmosphere. Again, that's on Earth, and that's because the pressure has to get bigger and bigger and bigger as it goes down into the fluid in order to keep that material be the same. What that means, though, is that for every point, let's say in this whole system above, that means that the pressure is less than 1 atmosphere. So a siphon only works when you therefore have the level of one bucket be quite a bit lower or even a little bit lower than the other one where the tube is in. And of course, it also requires you to fill the tube with water, which we were talking about. You might have to, suck it up or something like that, or I think I filled it from the sink, but that's the idea. So how does it work? Well, how it works is that if you imagine any chunk of fluid, and it has, say, differential pressure on it, especially if it's a pressure that's different than what is required just to hold it up from gravity, that means that where there's more pressure, the fluid's going to actually go this way. So if we apply that then to our siphon, let's draw the tube again. You can imagine something like this, right? And if you have, say, more pressure down here, so pressure against the fluid, P greater than 1 atmosphere, the pressure that is then less over here will cause then that fluid to flow. And so that's how the siphon works. So the siphon will stop, though, when you, say, get to a point where the pressure, the water starts here and goes to here. In that case, then, you have the same pressure, so no flow. So it's stopped, we saw, when you have two containers, and it doesn't actually matter where the containers are, but once the water level becomes the same, then you can still have the tube, but no water is going to flow. Okay. And then the last question was, how tall can a siphon be? And this is really the idea of a barometer, because no matter what the pressure is at the bottom, the very smallest pressure can be is a pressure of 0. And we know from hydrostatic equilibrium, so you can imagine even that you had, a little vacuum. Up there. And so the greatest that the pressure differential can be, delta P, is rho G delta Y. So if it's water, it's 1,000 kilograms per meter cubed times 10 meters per second squared, delta Y. And so that's why barometers are not often made out of water, because this is not a very big number. If you want to go from, say, 1 atmosphere to 0, and then you have 10 to the, let's see, 1, 2, 3, 4, let's call that pascals per meter times delta y, that means that delta y has to be something like 10 meters. So that's really, really very tall.